Hello, my name is Cameron Kettleslegger, and today I'll be walking you through how my research group was able to use diesel soot nanoparticles as a conductive carbon additive in lithium-ion batteries. A little background. Lithium-ion batteries are the most popularized form of portable rechargeable energy storage device in the past 30 years. Super P carbon is commonly used as a conductive additive within these batteries, but we found that diesel soot is chemically similar to Super P carbon. So we asked the question, can we use this industrial waste as a useful additive in lithium-ion batteries? So to do this, we set up two different types of electrodes, one for Super P and one for anneal diesel soot. The electrodes themselves are composed of 8:1:1 weight ratio of active material, conductive carbon, binder, and finally a solvent to bring everything together. Once constructed, they were put in a coin cell with 1 molar lithium perchlorate in 1:1 ECDMC, and with a counter electrode of lithium, pure lithium metal, to test them. We then conducted various tests, including galvanostatic charge-discharge tests, rate capability tests, and material characterization to get the data we needed for our study. If you look down here, this is the actual setup of our water batteries. So right here, if you can see these large blue dots, that's the active material. The small black dots are the conductive carbon. The gray around it is the actual electrolyte. And how we get to this point is from right here, we create our slurry and we let it cast and dry on an aluminum foil, which acts as our current collector. Then we punch 12mm discs out of them, which are the perfect size for a coin cell. Finally, we will conduct tests using an Arben system. Right here is our GCD curve. This red line right here is anneal diesel soot, which we found an average discharge capacity over 100 cycles to be 110 milliamp hours per gram. We found for Super P carbon, the industry standard, is 130 milliamp hours per gram. Even though these are slightly different, they're pretty close. So that's really what we want to see for a replacement material like anneal diesel soot. Regardless, looking at the Coulombic efficiency, which is the discharge capacity over the charge capacity, essentially how symmetrical is this material charging and discharging, we find 100% for 100 cycles. This means that this material is reliable and can withstand many cycles. So regardless, we conducted impedance spectroscopy to determine the internal resistance within our materials. While these are slightly different, the main fact here is that they're both under 100 real ohms on these humps. And that just simply means that there is little internal resistance and that our data that we've collected is solid. If you look over here, this is our rate capability test, in which we test at various C rates. A C rate of 1C means a full charge within 1 hour of a material's specific capacity. So we wanted to see how this changing charge and discharge rate would affect the capacity of the material. Throughout all this, as you can see, there's some disparagences along the way, but ultimately after 30 cycles of many different cycles, we see that a C/2 2-hour charge rate provides a 95% of the original capacity for both of the materials. That means that these are flexible materials. They can handle various charge and discharge rates. Regardless, let's look at the material characterization. Right here we have high-resolution transmission electron microscopy, in which we found an average particle size range of 20 to 200 nanometers. We verified this using some scanning mobility particle sizer spectroscopy, in which we found the exact range that we were looking for in the HRTEM photos. However, we found average particle sizes for low engine load to be about 50 nanometers, and for high engine load about 100 nanometers. Regardless, what we found through this study was that diesel soot is a viable alternative to Super P as a conductive carbon additive in lithium-ion batteries, and that there's industrial potential to use this waste as a useful battery component. Of course, we need to study some things in the future, which is, can we use this soot as an active material and not just a conductive carbon? Also, can this work in different battery styles? Say a sodium battery or a potassium battery even, But regardless, I'd like to thank the Wentz Foundation for their contributions to me and this project. I couldn't have done it without y'all. Y'all are helping me make my ends meet. Regardless, I would like to thank OSU's Chemical Engineering Department, as they provided all the tools I needed to conduct the tests that you all want to see. Also, I'd like to thank the University of Southern California Physics Department, as they contributed much to this project in terms of mental contribution and writing contribution. Thank you, and have a nice day.